What up, nerds, and welcome to Earth's Ocean. Okay, so this is going to be the first in a series of video lectures for my Earth Science classes. So let's go ahead and get started. Here we go. All right, so we're going to be moving on from freshwater, like we were on before. We're going to be talking about oceans and oceanography. So, oceanography, as you might expect, is the study of Earth's oceans. Okay, and an important thing to know about oceans is kind of like what we've already talked about. Is it is most of the water on Earth is there in the oceans, about 98% of it, almost 97.5. There's one of two ways it could have come: either comets hitting the Earth, or volcanic eruptions emitting gases into the atmosphere. Probably both, actually. Probably both. So either comets coming, hitting Earth, and bringing water with them, and water going up into the atmosphere, or water that was trapped in Earth's surface, or excuse me, underneath Earth's surface, that came up during volcanic eruptions and converted into H2O, into vapor, which then rained down. And you wouldn't think about it, but raining over billions of years, that's going to create some oceans. Okay? So, oop, all right. So today we can use sonar, and satellites to study the ocean. Satellites such as Topex / Poseidon monitor the ocean's surface, the temperatures, the currents, wave conditions. Sonar, as you can see down here, allows us to map the ocean floor. Okay, as I said, oceans cover approximately 71% of the Earth's surface and make up right around 98% of all of Earth's water. Okay, you see this for the hemispheres. 61% of the northern hemisphere, 81% of the southern hemisphere. If Antarctica wasn't there, which a lot of people forget that it is, okay, all we would pretty much have down here is ocean. Okay, so what makes seawater salty? It's a question I get a lot whenever we go over ocean stuff. So ocean water is made up of several different elements, okay? Primarily it is water, but what is dissolved in there is a lot of sodium, a lot of chloride, which should make sense. Sodium chloride is salt. NaCl is salt, straight up salt, like you would have at your table. But there are also other elements like magnesium, sulfate, very small amount of calcium, and a small amount of potassium, as well as less than 1% of any other kind of things that might dissolve in there. Okay? Now, when we talk about seawater, we need to talk about a couple chemical properties, okay? So salinity is a word, it's a term that means how much dissolved salt is in the water. And salinity is measured in grams or kilograms, okay? Usually it's grams of salt per kilogram of water, or parts per thousand, PPT, okay? So remember that, parts per thousand, all right? And if we look at this, we can actually see differences in ocean salinity in different areas. So all of these values are given in parts per thousand, as you can see. But on this map, close to the north of here, up by Alaska, it's actually less salty. It's right around 32 parts per thousand. Whereas in the saltiest places, it's going to be right here off the coast of South America, of Brazil, or right here, right in the middle of the Atlantic Ocean between North America and Africa. It's at 37. So you're not seeing a huge difference anywhere in the oceans, but there's a difference. Average salinity of seawater is right around 35 ppt, or 3.5%. So mostly water, but still about 3.5% of the salts. And again, this is lots of different things. It's not just sodium and chloride. It is also sulfates, calcium, magnesium, like I said, all those other things. Okay? So, how do you add salt in? How does some water get more salty? How does some get less? So, salinity can be increased by weathering or erosion of rock. Okay? Which should make sense because the salts can come off of the rock and go into the ocean itself. Volcanic activity, that's going to be adding it directly into the ocean water from the minerals that are being erupted. And then evaporation. So as the water goes away, what's left behind is the salt. Okay, so normal evaporation, you've got, the water right here, and as the water goes away, all the salts are left behind. Salinity goes down by precipitation, so adding fresh water back in, runoff from freshwater sources, so rivers leading into the ocean, and then icebergs and sea ice melting, so anywhere near Antarctica or in the polar ice caps, as that melts, all that is fresh water, so that would decrease salinity, make it less salty. Okay, so the ocean can be divided into a number of layers. Okay, so 3 basic layers based on temperatures. This is actually how we divide our ocean. Usually based on temperature. A lot of people think it's based on light, and there are divisions based on light, but it's on temperature is what we're going to be worried about for this video. So the surface layers right up here, nice and warm. Okay, this area is called a transitional thermocline. Okay, therm means heat or temperature. Cline is usually going to mean a change over some distance. So a decline or an incline. So this is a thermocline, a change in temperature in the bottom layer down here. Okay, here you go. Thermocline is a zone of rapid temperature change. So as depth increases, temperature decreases. And that is because of the lack of light that is able to penetrate that deep. The light filters in just so far, and after a little while, it can't diffuse anymore. So no light gets down there. And if there's no light down there, it can't transfer into heat. Okay, so it gets quite cold. So the surface layer is relatively warm. See, so temperature in degrees Celsius. So surface layers in some areas, okay, we see is up to 24 degrees Celsius. It's pretty warm. That is pretty warm. That's close-ish to room temperature, I'm pretty sure. And then you've got a very rapid thermocline, and then you've got this bottom layer, and you're going to see really, really cold temperatures, much closer to almost freezing. Okay, 0 degrees Celsius. So going along with temperature and salinity, okay, how hot, cold, salty the water is, you're going to see different densities. Okay, water density is very affected by temperature and salinity. So cold water is more dense, and so it sinks to the bottom. Warm water is less dense, and that should make sense, right? If you think about it, here I'm going to make myself bigger real quick. So if you think about it, warm water, what warm temperatures do to any fluid is it makes it move around more, and as it does that, they're going to be going like this, right? Moving past each other. The denser you get, excuse me, the colder you get, the more dense it's going to be, the closer together they are. And as we talked about before with magma under the Earth's surface, density causes it. The denser something is, the more it sinks. Less dense something is, the more it rises. And so when you put those two together, as long as you've got a source of heat, you get convection currents. So let's go back. Okay. So warm water is less dense, it rises. Cold water is more dense and sinks. Higher salinity leads to increased density. That's just because there's more stuff actually in the water. Instead of it just being water, there's other things too, which makes it more dense, makes there be more particles in between. And higher density water sinks. So the saltier it is, the denser it is. Okay? So if you were to put all these together, if you were to layer them out, okay, this red layer would be warm, fresh water. So it is warm, making it less dense. It's fresh, no salt, making it less dense. It's all the way at the top. Yellow is cool, fresh water. Fresh water is always going to be less dense than salty water. Always. It's always going to be less dense than salty water. Green, this layer right here would be warm, salty water because it's warm. It's a little bit less dense than the cold. And then blue would be your cool, salty water. Okay, and the reason all this is important is because in this test tube, it's very easy to see it like that, but on a global scale, you're going to see these different densities interacting, and that's what causes the currents and the shifting waters of the world. Okay. All right. Yep. So it causes the currents. So density currents are caused by the differences in temperature and salinity in the deep water. These are your ginormous, huge currents as the ocean is shifting. And then surface currents are caused primarily by wind. So wind also goes through these convection things, and that can pull the water along in one direction as it does, causing a surface current. So the Gulf Stream, this is cold and salty. Okay, it's very dense water. In the North Atlantic Ocean, the water becomes so dense that it begins to sink down through the less salty and less dense water. This causes a density current. So from North America to Europe, it follows the westerlies as a surface current. Okay, so basically, as you can see here, right in these areas, okay, so way down here and way up here is going to be quite cold. So if you follow these arrows, I know they're a little blurry, kind of hard to see, but if you follow these arrows, warm water shifting around, hitting colder areas and sinking, becoming more dense, and then moving through other areas and warming up. Basically, all you really need to know there is that the Gulf Stream is an example of a density current because cold, salty water sinks underneath the warmer water. There's a couple other things we need to talk about. One is called, where's my mouse? Come back. There we go. One of them is called gyres. These are circular ocean currents caused by land masses. So this happens here in the North Atlantic and the South Atlantic. And then there's larger ones in the South Pacific, as well as in the North Pacific, and then one in the Indian Ocean. Okay, there's upwelling. This is vertical movement of ocean water. This is when it hits a continental plate, it'll go all the way up, blast its way up like that, and that'll kick it back the other direction, causing currents as well. Or any current that is, or any wind that is pulling the surface water away. Well, you're going to see that the ocean water is going to be pulled up to fill the space. Okay, which should make sense. Now, the Coriolis effect is it's a really interesting idea. So this says ocean currents in the northern hemisphere are deflected to the right, and currents in the southern hemisphere are deflected to the left. So as the Earth spins, okay, the Coriolis effect essentially makes it so that anything that isn't tethered down and actually attached to the Earth is going to be affected by that spin. So the way to think about it, I'm going to make myself big again. The way to think about it is, if this will be my example, is if this is the Earth, okay, and I decide I'm going to point in one direction. I'm not tethered to the little jar here, but I'm pointing in one direction. Well, the jar is spinning, okay? The Earth is spinning. So I'm going to make it spin in one direction. I'm going to start here, and we're going to see where I ended up. Okay, so that is where I ended up. That is where I started. I went in a straight line, but as you can see, I ended up about a quarter of the way around the jar. Because the jar was spinning, that is the Coriolis effect. So water in the ocean is not exactly attached to the surface of the world, so it is also going to be subject to the Coriolis effect, where it is going to be kicked off one direction or the other because of the Earth's spin. Now, if you aren't fully comfortable with the Coriolis effect, I suggest looking it up and getting a little bit more comfy. Okay. All right, we've got tides. Tides is the rise and fall of ocean levels. This is primarily caused by the moon. Okay, so as the Earth is spinning, the moon is going around it, kind of like this. And as that happens, it's going to be pulling on the ocean, as well as having the sun have its own gravity pulling on the ocean as well. So it's going to cause high tide at certain times of the day and low tide at other times. Now we've got neap tides and spring tides. I don't really want you to worry about this too much because we're going to hit it again in astronomy. So for now, that is it. Thank you guys for watching, and stay wonderful. Gucci.